In this final video, we are going to see the definite integral in action by actually looking at an application problem, kind of a real-world problem. The problem is this. Suppose the amount of water leaking from a tank in gallons per minute is given by this following function. I should say suppose the rate of water leak. It's not the amount. Let me change that. It'd be like the rate of change of water. So suppose the rate of change of water leaking from a tank is given by this function. So this is the rate of change of the water. Okay? It wants to know how much water leaks out in the first 10 minutes. How much water leaks out in the second 10 minutes. If the tank holds 15 gallons of water, then how long does it take for all of the water to leak out? And then what is the average rate of change of the water leakage during this time? Okay, so this is a function of the derivative. So if capital F of x here, right, capital F of x would be amount of water in the tank. At time x or whatever. Okay, at a given time, that gives the amount of water in the tank, and the water is leaking out. If you take the derivative, this is the rate of change that the water is leaking out. Okay, and if I want to find like the total amount of water, how much water leaks out in the first 10 minutes, that is a definite integral. Okay, that would be the integral of 0 to 10 of the rate of change, 25 over 1/2 x plus 3 squared. Okay, so this would involve a u substitution. So I would let my u here equal 1/2 x plus 3, so my du would be 1/2 dx, so 2 du is equal to dx. Okay, so it's a fairly simple substitution. I can put u in here now, so this would be the integral from so I need to update the limits here, so I'm going to plug 0 into here, and when I do, I get 3 for the lower limit. When I plug 10 into here, I get 5 plus 3, so I get 8. So my new limits are 3 to 8, and I would have 25 over, this would be u squared, and then I would have a 2 du here. Okay, so now what I'm going to do is I'm going to bring out the constant, and so 25 times 2 is 50, so I'd have 50, 3 to 8, and then this would be u to the negative 2 du. And so now I can find the antiderivative to that. So that's using the power rule. So it would be 50, and this would be u to the n plus 1 over n plus 1. Well, n plus 1 is negative 1, so this would be u to the negative 1 over negative 1. And then it would be from 3 to 8. From 3 to 8. Okay? And so now, so this would just be, I could rewrite this as negative 50 over u from 3 to 8. And so now I can plug in 8 and then plug in 3. It would look like that. And then this, I could rewrite this minus a negative makes that positive, so I could write that as 50/3 minus 50/8. And then common denominator of 24. So if I get a common denominator, I have to multiply top and bottom by 8 here, and so I get 400 minus top and bottom by 3, 150 over 24. I'm going to just fit it in. So that would be 250 over 24 is what I get. A little over, this is like a little over 10 gallons leaks out during that first 10 minutes. Okay? The tank holds 15 gallons. I have to share the story. I remember when I was taking calculus, right around that time when I was taking calculus, the movie Titanic came out, and I remember watching that movie, and the engineer of the ship was on the person that designed the ship or whatever was on there, and he was sitting there doing math to figure out how long it would take for the ship to sink. And so he had some complicated calculus on there. Just for a second it showed that. And I just remember thinking, oh my word, I could never have done that. I'd be in panic and my brain wouldn't have been able to think straight and work through all that. I don't know, I just had to share that story. I remember thinking that. Okay, so now what about the second 10 minutes? So this would be 10 to 20, right? Of this 25 1/2 x plus 3 squared, and that would be dx. And then I could do this change, but now I have to change these limits. So if I put in 10 into this, I would get 8, so this would be 8. And if I put in 20, I would get 13, so 8 to 13. And then you would have, this would be like, 50 u squared du. And so I would get negative 50 over, negative 50 over, I'm just thinking about the Titanic. No, I'm just kidding. Negative 50 over u from 8 to 13. And then I could rewrite this here around, so it'd be the 50 over 8 minus the 50 over 13. So I'm just plugging it in and switching it around. And then I would need a common denominator. I'm going to use my calculator here, if it holds up. Let's see, 50 divided by 8 minus 50 divided by 13 gives us this number, which is pretty small, 2.40. Let's see if it can get that fraction back. Ah, and it did. So it's 125 over 52, which is approximately like 2.40 gallons. So about a little over 10 gallons went out during the first 10 minutes, but a lot less went out during the second 10 minutes. And so a lot less is going to go out during the third 10 minutes, right? And so we're up to like around 13, and so there's still 2 more gallons to go, and we want to find out how much is it going to take in order for the tank to be empty. So what I'm really asking here is the following. This is you can call this an integral equation. From 0 to what value, 0 to t, will this integral equal 15 gallons, right? So I got to get that antiderivative. And so what I'm going to do is I'm going to I'm going to say that this antiderivative, or the indefinite integral of this, the indefinite integral of this is going to be basically it's going to be this here with the u substituted back in. So it's like negative 50 over 2 or 1/2 x plus 3. So that's just plugging that back in. So then you'd have plus c. So this is the antiderivative, okay? And what I'm going to do then is just use this antiderivative. I don't need the plus c because I'm going to use the fundamental theorem, and if you subtracted one antiderivative minus the next antiderivative, the c's would cancel out. So what I'm going to just do is I'm going to say that this whole thing here is this part of the antiderivative evaluated at 0 and at t, okay, and that's going to equal 15. And so now plugging this in, so if I plug in t, I'd get negative 50 over 1/2 t plus 3 minus, and then I'm going to plug in 0. So negative 50 over, and if I plug in 0 here, I just get 3. And that's equal to 15. Okay, so now I could rewrite this 50 over 3 minus 50 over 1/2 t plus 3 is equal to 15. So basically what I'm doing is I'm finding what t value makes that equal to 15, and I'm going to do it by solving this equation here. Okay, so now I'll bring this over here, and then the 15 over there, so 50 over 3, and the 15 over 3 would be minus 45 over 3 is equal to 50 times 1/2 t plus 3. And so this basically, this is 3. So this basically is 5/3 is equal to 50 over 1/2 t plus 3. And now I'm going to cross multiply. 5 times 1/2 t plus 3 is equal to 150. Now I'm going to go up here, and this would be 5/2 t plus 3, or plus 15, is equal to 150. And then I can move the 15 to the other side, so 5/2 t is equal to 135, and so my t is equal to 135 times 2/5. So so 135 times 2 divided by 5, and you get 54, and so it's 54 minutes is how long then it would take. So the first 20 minutes gets about 13 of the gallons out, but you see that the rate at which the water is leaking out is decreasing. As this number gets bigger, the rate is decreasing, and so it would take about 54 minutes then for the water, in fact exactly 54 minutes for the water to leak out. And actually, let me do math, and then we will actually, let's see if I solved my equation right. I'll do the integral from 0 to 54, and then we'll do 25 divided by parentheses 0.5 x plus 3 parentheses squared, all with respect to x, and then hopefully this equals 15, and it does. It equals 15. So that's how long it would take then for all of the all of the water to leak out, okay? And then it wants to know, the last thing was, what is the average change rate of, what is the average rate of change of the water over the time it takes it to leak out. So 15 gallons leaked out in 54 minutes. Okay, and that would mean that you would have 15 divided by 54, and you would get 15 divided by 54, you know, about 0.27 repeating. So what would the math be here? Or what would the fraction be? It's like 5/18. So 0.278, we'll just write it like that, gallons per minute. Okay, so what I wanted to do here, though, is the reason I asked, like, why did you ask that? That's how much it would be on average, okay? The reason I asked, that I did this is one thing I haven't shared yet, because I wanted to get directly to the definite integral, didn't want to get sidetracked too much, but the average value of a function, or the mean value of a function, is given by the following. The average is equal to 1 over b minus a times the integral of a to b f of x d of x. So if you take the integral from a to b and divide it by 1 over b minus a, this gives you the average value of the function. Okay, so another way of thinking about it is you're actually finding the value that it would take to estimate or to give the definite integral. So kind of like when we proved the fundamental theorem. So in other words, if this is your function here from a to b, so your function from a to b has a certain area, and that area is equal to the definite integral, right? The average value here is going to be some value, and this is kind of like what we did in the fundamental theorem. It's going to be the value that's going to give you the same amount of area by finding the area of the rectangle. If you use that value through the whole thing, it would give you the same amount as you would get underneath the area. So in other words, this average times the length of the interval is equal to the area underneath the function at that value. And they call that the average value of the function. Another way to think of this is if you wrote it like this, the average is equal to the sum over the number of values, right? Well, if you write this expression here as a to b f of x d of x, and then b minus a on bottom, the top here is like the sum. You're summing up all the values, all these f of x's, right? And then the b minus a is like the number. That length of the interval is kind of like the number of f of x's that you observe. So you sum up all these values. There's an infinite number of them, right? And then you divide by the length of the interval is like the number of them, and you get the average of value of the function, which if you use that for a rectangle, it would give you the same sum as the area here. Okay? So this idea of the average value of a function is kind of important. It was actually used to prove, you use that sort of idea in the proof of the fundamental theorem of calculus, when we found the value that gave us the area, so that we could simplify the difference quotient of that area function. So I just thought I would end on that. Now let me tell you, I didn't tell you this at the beginning of the video because I wanted you to watch this video, but there was no problems on the homework over the definite integral that were like this, where you actually use the definite integral to solve problems. And that frustrates me. I considered doing a worksheet with some of my own problems, but I figured with me leaving and wanting to get everything up, and you already having a lot to do with this section, I would just skip that, not worry about it. So there aren't really any problems on the homework. The closest thing is in the very first section of chapter 5. It was actually a leaking aquarium that kind of used this idea, but you were doing a finite sum. Okay, well this is what it would be if you were given the function of the rate at which it was leaking. This is what the math that you would use. That's the closest thing. There wasn't really anything in this chapter. That was kind of frustrating. I'm sure when you get to Calc 2, this book has application problems involving the definite integral, but they would look like this. But you actually don't have any of these on the homework, but I knew if I said that at the beginning of the video, you may not have watched the video. So I'm telling you at the end, and that is actually the end of the entire chapter here, the end of the course, the end of Calc 1. So I hope you enjoyed it, hope you learned a lot, and I suppose I can say goodbye. How do I do this? There we go. Okay. So, good luck. Enjoy the rest of your summer, and thank you for all your hard work. I hope you had a good experience doing Calc 1 online in the summer, which is I couldn't have imagined doing that myself. This has not been easy. I'm sure if you've really poured yourself into this, and I know some of you have been working very hard. So thank you very much. I hope you enjoyed the class, and if you're moving on to Calc 2, good luck with that. So thank you.